Last class we learned high availability and AT212, how to keep a system up when its parts fail. Today, we tackle the other half of running a real system in the cloud, how to keep it fast when the amount of work changes. Because here is the thing about real systems and 8.2.2.4. The load on them is never flat. A shopping site is quiet at 3 am and swamped during a festival sale. A news site trickles along until a big story breaks and traffic explodes tenfold in minutes. Demand surges and it fades constantly. And that poses a genuine problem. If you build for the quiet times, your system collapses the moment a rush arrives. If you build for the peak, you are paying for a huge amount of capacity that sits idle almost all the time. Fixed capacity is always the wrong size, and A212 either too small and it crashes, or too big and it wastes money. Scaling is the answer to this problem, and it is one of the cloud and P9's greatest superpowers. Scaling means growing your system in D39's capacity to meet rising demand and shrinking it back when demand falls and A200, ideally automatically. Today, you will learn the two ways to scale, how auto-scaling works, what triggers it, and the one design principle and A200 statelessness and A200 that makes it all possible. Let us learn to grow and shrink on demand. Here is our path for today. First, why scaling is necessary. Second, vertical versus horizontal scaling. Third, auto-scaling. Fourth, scaling triggers. Fifth, scaling out and back in. And sixth, stateless design. Let us dive in. Let us start by feeling the problem clearly. Because scaling only makes sense once you see how badly fixed capacity fails. Picture the load on a typical system over a day or a week. It is a wavy line and 8 to 12, low at night, rising through the morning, spiking at peak hours, calming down again, with the occasional dramatic surge when something goes viral or a sale begins. Demand is a moving target that swings widely, sometimes by 10 times or more between quiet and peak. That variability is the fundamental fact your system has to cope with. Now suppose you provision a fixed amount of capacity and AT112, a flat line of servers. Set that line too low to save money, and when a surge crosses it, your system runs out of capacity and falls over, pages time out, users get errors, and you lose customers at the worst possible moment, right when they most wanted to use you. Fixed and small means crashing under load. So you might set the flat line high instead, above even the peak, to be safe. Now the system never crashes on 82.5, but look at all that capacity sitting above the actual demand for the vast majority of the time. At 3 am, with almost no traffic, you are still paying for enough servers to handle a festival rush. That gap between your fixed capacity and the real lower demand is pure waste and 8112. Money spent on machines doing nothing. Fixed and large means paying for idle. Either way, a fixed size is the wrong size almost all the time, because demand is not fixed. What you actually want is for capacity to follow demand and 8.212 to rise with the surge and fall with the lull and 8.212. And that is exactly what scaling gives you. So the takeaway, real system load varies constantly, often by 10 times or more. So fixed capacity is always the wrong size and A212. Set it low and a surge crashes the system. Set it high and you pay for idle capacity most of the time. Scaling solves this by making capacity follow demand up and down. There are two fundamentally different ways to scale a system, and understanding the difference is essential because the cloud strongly favors one of them. The first is vertical scaling, sometimes called scaling up. This means making your existing machine more powerful and AT012, adding more CPU, more memory, upgrading to a bigger B5 server. You keep one machine and you make that one machine stronger. It is intuitive and simple. Need more power. Get a bigger box. For a while, this works nicely, and for some workloads, it is the right choice. The second is horizontal scaling or scaling out. Instead of one bigger machine, you use more machines and A212. You add additional servers that work together, sharing the load between them. Rather than one powerful box, you have many ordinary boxes running in parallel. Need more capacity? Add another server and another, spreading the work across all of them. This is the model the cloud is built around, and it is the one we focus on today. Why does the cloud favor horizontal scaling? Because vertical scaling has a hard ceiling. There is only so big a single machine can get. Eventually, you hit the largest server available, and you simply cannot scale up any further. N80 halve, you are stuck. Horizontal scaling has no such wall. You can keep adding more machines, essentially without limit, to handle almost any amount of load. The giant internet services handle billions of users precisely by running enormous fleets of ordinary machines, not one impossibly large computer. Horizontal scaling also pairs perfectly with the redundancy and load balancing from last class and A200 tool. Many machines behind a load balancer are both scalable and highly available at once. So while vertical scaling is simple and has its place, horizontal scaling is the cloud way. Scale by multiplying machines, not by enlarging one. So the takeaway, vertical scaling means a bigger, more powerful single machine, an A212, simple but capped by the largest box available, an A212, while horizontal scaling means more machines sharing the load, which has essentially no ceiling and pairs with load balancing for scale and availability together. The cloud is built around horizontal scaling. Horizontal scaling lets you add machines and 82-valve, but who decides when to add them, and does it? In the cloud, the answer is auto-scaling, and it is genuinely magical to watch. The naive approach would be to have a human watch the load and manually add servers during a rush and remove them afterward. But that is slow, error-prone, and impossible at 3 am or when a surge hits in seconds. Auto-scaling replaces the human. It is a cloud service that continuously watches your system in TT9 SES load and automatically adds or removes machines to match it. An 8200, no clicks, no on-call engineer, no delay. Here is how it behaves. When the load on your servers rises, an A12 a surge of traffic comes in, an A12 the autoscaler notices and automatically launches additional instances to share the increased work, expanding your fleet to handle the rush. Your capacity grows within moments of the demand growing, so users stay served and nothing falls over, even as traffic climbs. And when the load falls again, an A212, the surge passes, the night grows quiet, and A212, the autoscaler notices that too, and automatically shuts down the now unneeded instances, shrinking your fleet back down. You stop paying for machines you no longer need the moment you no longer need them. This is capacity following demand in real time, with no human in the loop. It grows when you are busy and shrinks when you are quiet, all by itself. This automatic, responsive elasticity is what people mean when they call the cloud an A200, elastic, LA200, and it is one of the single most valuable things the cloud provides. You define the behavior once, and the system right-sizes itself forever after. So the takeaway, autoscaling is a cloud service that continuously watches your load and automatically adds machines when demand rises and removes them when it falls. NA212, capacity following demand in real time. With no human deciding or clicking, an 81-valve, which is the elasticity that makes the cloud so powerful. For autoscaling to work, it needs to know when to act. You tell it by defining triggers, an 80/001, and understanding this makes autoscaling concrete rather than mysterious. A trigger is based on a metric, a measurable signal of how busy your system is. The most common is CPU utilization, and ATR12, how hard your servers and 3T9 processors are working, and ATR12. But it can be many things: the number of requests per second, the length of a request queue, memory usage, or a custom measure that reflects your particular load. The autoscaler constantly measures this metric across your fleet, so it always has a live reading of how busy you are. Then you set a rule around that metric, usually with a target. For example, an A200, keep average CPU around. Scale out, an 8 to a 20 on, the rule connects the metric to an action. when the measured value crosses your threshold. The autoscaler adds or removes capacity to bring the metric back toward the target. You are essentially telling the system what an 8200, too busy and 8200, 200, and 8200, too idle and 8200, 200, 200, 200 mean for you in numbers. What makes this so powerful is that you configure it once, declaratively, and it runs forever. You do not script every scaling action. You state the goal N80 at N8 N8 keep CPU near 50% N8 N8 and the autoscaler continuously does whatever it takes to hold that goal, adding machines in a surge and removing them in a lull day and night. It is the same declared, desired state thinking that runs through modern cloud infrastructure. You describe the outcome you want, and the system maintains it. Choose a metric that truly reflects your load, set a sensible target, and your system will keep itself right-sized automatically. So the takeaway, autoscaling acts on triggers, an 80:1, a metric like CPU usage or requests per second that measures how busy you are, and a rule with a target that says when to add or remove capacity, an 80:1, and you configure this once, declaratively. So the autoscaler continuously holds your system near the targeted in a surge and a lull alike. Let us emphasize something crucial that people often half forget: scaling is a two-way street. The savings come from scaling in as much as the reliability comes from scaling out. Scaling out is the direction everyone thinks of first. When demand surges, you add machines to your fleet to handle the extra load. The sale begins, traffic floods in, and the autoscaler launches more instances so that the growing crowd is served smoothly. This is what keeps your system fast and standing during the busy moments and AL2112, the expansion that meets the rush. Without it, peaks won't crush you. But scaling in NA812, the reverse NA812, matters just as much for a different reason. When demand fades, you remove the machines you no longer need. The sale ends, the night falls, traffic drops and A212, and the autoscaler shuts down the excess instances, contracting your fleet back to a small size. This is what saves you money. You are no longer paying for a festival-side fleet during a quiet Tuesday night. Scaling in is where the cost efficiency of the whole approach is actually realized. Together, these two directions are the entire point of elasticity, and they map directly onto the cost benefit of the cloud. You get reliability from scaling out an 8112, always enough capacity for the peak in 8112, and you get economy from scaling in an 8112, never paying for capacity you are not using. A system that only scaled out would stay expensively large forever after its first surge. A system that only scaled in could never handle a rush. It is the combination an A212, grow for the peak, shrink for the lull, automatically an A212, that gives you both performance and cost efficiency at the same time. That is the promise of the elastic cloud, fully delivered only when you use both directions. So the takeaway, scaling goes both ways and A25 pool. Scale out by adding machines to meet a surge, which gives reliability, and scale back in by removing them when demand fades, which is where the cost savings are actually realized. Using both directions is what delivers performance and economy together, the full promise of cloud elasticity. There is one design principle that makes all of this scaling possible, and if you ignore it, auto-scaling simply will not work well. That principle is statelessness. Let us understand why it matters so much. Think about what happens when the autoscaler removes a machine to scale in, or when a load balancer sends your next request to a different server. If that server was holding something important that only it knew NDA212, your logged-in session, your shopping cart, some data kept only in its memory NDA212, then removing it loses that data, and sending you to a different machine means the new one has no idea who you are. A server that holds per user state like this is called stateful, and stateful servers are painful to scale. You cannot freely add or remove them because each one holds something irreplaceable. The solution is to design your servers to be stateless and A212, to hold no per user session data themselves. Instead, any state that must persist and IA to IE sessions, cards, user data, and IA to IE to IA is kept in a shared place that all servers can reach, like a shared database or cache, rather than in any individual server on 39.9 memory. Now, every server is interchangeable. None of them holds anything unique, so any machine can handle any request equally well by looking up whatever it needs from the shared store. The servers become simple, identical workers. And this is precisely what makes scaling painless, because the servers are stateless and interchangeable. The autoscaler can add a new one, and it can immediately start handling any request and 84 to fall. It needs no special knowledge. It can remove one and nothing is lost, because that server was holding nothing unique. The load balancer can send each request to whichever server it likes, because they all behave identically. Statelessness is the quiet foundation that lets machines come and go freely, which is the entire basis of elastic scaling. So when you build for the cloud, keep your application server stateless and push state into shared services and 8212. And scaling, load balancing, and self-healing all fall into place effortlessly. Forget it, and none of them work smoothly. So the takeaway, scaling works cleanly only if servers are stateless and 8512, holding no per-user session, with any needed state kept in a shared database or cache, and 8512, because then every server is interchangeable. So the autoscaler can add and remove machines freely, and the load balancer can route anywhere. Statelessness is the quiet foundation of elastic scaling. Before we recap, let us watch the whole thing work together in a single story, because seeing the pieces cooperate is what makes it click. It is a normal evening, and your system is running a small fleet of, say, 3 stateless servers behind a load balancer, quietly handling light traffic. CPU sits comfortably around 40% below your target, so the autoscaler is content and does nothing. Everything is calm, and you are paying for just 3 machines and 8212, exactly what the light load needs. This is the efficient baseline that scaling in gave you after the last busy period. Then a sale launches and traffic surges. Requests pour in, the servers work harder, and CPU climbs past your target of 50% toward 80. The autoscaler, watching that metric, springs into action. It launches new instances and A212, 4, 5, 6 more, and A212, and because they are stateless, each one immediately starts taking requests the moment it is ready. The load balancer spreads the flood across the growing fleet. CPU settles back down toward the target, and users sail through the sale with no idea how close it came to overload. Your capacity grew to meet the demand automatically in minutes. Hours later, the sale ends and traffic drains away. CPU drops well below the target across the now large fleet, and the autoscaler responds again, this time by shutting down the excess instances one by one and A212 for removing them safely, because none held any unique state, and A212, until you are back to a lean handful of servers for the quiet night. You never crashed during the peak, and you are not paying for the peak now that it is over. That full cycle, and 8212, calm baseline, automatic scale, out for the surge, automatic scale in afterward, all on stateless servers behind a load balancer and 8212, is elastic scaling in action. And it is how modern systems stay both fast and affordable under wildly varying load. Everything today comes together in that one smooth loop. So the takeaway, it all works together as one loop, and A212, a lean baseline of stateless servers behind a load balancer, an automatic scale-out that launches interchangeable instances when a surge pushes the metric past its target, and an automatic scale-in that removes them when demand fades, and 8-hole, keeping the system fast through the peak and affordable in the quiet, with no human in the loop. Let us close with the habits that make scaling reliable in practice, because the concepts are simple, but a few disciplines separate smooth scaling from painful surprises. First, prefer horizontal scaling and build stateless. Design your application servers from the start to hold no per-user state, pushing sessions and data into shared services so that scaling out and in is always an option. If you bake in statefulness early, you will fight it forever. If you build stateless from the beginning, elasticity comes almost for free. This is the foundational habit, and it is a design decision, not an afterthought. Second, scale on the right metric and give yourself headroom. Pick a metric that genuinely reflects your load and ATU fun often CPU or request rate and ATU fun and set your target with a margin below the breaking point. So the autoscaler starts adding capacity before you are in trouble, not after. Now, base scaling takes a little time and AT new machines need seconds to start and AT so you want to trigger the scale out early enough that the new capacity arrives before the surge overwhelms you. A target that is too aggressive scales too late. And third, remember to scale in and test your scaling. Make sure your rules actually shrink the fleet when things go quiet, or you will quietly pay peak prices forever. And 82 hand dual, the scale in is where your savings live. And test the whole thing. Simulate a surge and confirm your system really does scale out in time and back in afterward before a real festival sale is your first test. Build stateless, scale on a good metric with headroom, and verify both directions work, and A200-212. Those habits turn elastic scaling from a nice idea into a system you can trust under any load. So the takeaway, scale well with 3 habits, and A2112, build stateless, and prefer horizontal scaling. So elasticity is always available. Scale on a metric that reflects load with enough headroom that capacity arrives before trouble. And make sure you scale in and test both directions, and A212, turning scaling from a concept into a system you can trust under any load. Let us gather the whole class in one breath. Scale because demand varies, and A212, fixed capacity either crashes under a surge or wastes money on idle. Vertical scaling is a bigger machine, capped by the largest box. Horizontal scaling is more machines, the cloud way almost without limit. Auto scaling watches your load and adds or removes machines for you, automatically in real time. It acts on triggers, and AT112, a metric like CPU, and a target that says when to scale. Scaling goes both ways, and A2212, out to meet a surge for reliability, back in when quiet for savings. And stateless design, holding no per user state, is what lets machines come and go freely. Next class, NAD12, databases in the cloud, manage data at scale, one idea at a time. That is scaling an A200